हेलो, ठीक ठीक। बस मेन प्रॉब्लम क्या रहता है कि कभी मान लीजिए डिस्कनेक्ट हो गया तो फिर वो चला जाता है, बाकी तो मैनेज हो जाता है। तो उस टाइम पे बस, हाँ, नहीं नहीं, वो तो दे देते हैं, वो थोड़ा एजेड है तो मैनेज नहीं कर पा रहे हैं, इसलिए तो दिया है उनको। और एक और हमारे साथ में है फैकल्टी, उसको भी दे देते हैं। तो लेकिन बाई चांस कल ऐसा हो गया था, एक दूसरे के पास चला गया था वो तो, हाँ, उसका एक्सेस। चलिए,
Good morning, sir. Very good morning.
very good morning, sir.
Yes. So we are entering the 4th day. We have finished 3 days very successfully.
Yes, sir. Yes.
Nice to know your students are all getting interested in this very important topic. And of course, now we also want to emphasize to them that the core engineering areas. Yeah.
So I also discussed with the participants yesterday.
Okay.
So they requested to repeat or to again show them the basic.
Sure. We are delighted to do that for them.
Yes,
and
yes.
We also want to emphasize to them that a lot of newer opportunities are coming in our core engineering areas, because everybody thinks it is only computer science or IT which will be in software. But a lot of our core engineering areas are also coming under this umbrella now.
Right.
So, a lot of opportunities. And example is the students who did this project today are all working on some real high-end jobs in their own domain.
Right.
Right. So one of them is in Tata International Communications at Singapore. He's the deputy general manager. He has risen to that extent, and he said, "Sir, this small project was what really took us in the initial one." The other man is a big manager in Cisco.
Right.
He is operating that, a lot of networking areas. The third boy is in avionics area, where he is able to utilize this. Fourth of them is in BHEL, again, this domain area. So that way, plenty of opportunities coming up for them. Only thing, they have to utilize it.
Yeah, they have to learn and then make use of that. That is the main thing. So things are available, but only thing how they are utilizing and getting into it. So that is the main thing. So sir, we will wait for some 5-6 minutes.
No problem.
Meanwhile, I request all the participants who have already joined, if they have anything to discuss with sir, they can unmute and ask the question directly. So all participants are welcome to this 4th day of the webinar. And very good morning to all. Sir is with us.
Yeah, I have my good morning and namaste to all of the participants. And we are really delighted that even on Saturdays and Sundays, our students are showing a lot of interest.
Right, sir, right.
Really nice of them. And we will wait for them. But of course, if there are any questions, I would definitely like to. Even otherwise, they can send it by our email.
I will share the mail also, so they can later on also they can communicate.
Also, they can come back.
Yeah. Ashish, you can ask. Ashish Bhatt. P. Sri Lakshmi. Then Nikhil Piparia. निखिल किस कॉलेज से हैं आप?
सर विक्रांत ग्वालियर।
विक्रांत ग्वालियर, हाँ हाँ।
यस
तो अगर कुछ आपका डिस्कशन हो तो आप पूछ सकते हैं सर के साथ।
सर वैसे मैं अभी 3rd ईयर में हूँ सर, 6M
राइट,
इलेक्ट्रिकल ब्रांच से सर।
इलेक्ट्रिकल में। अच्छा,
यस यस। अभी तो मैं सर आर्टिफिशियल इंटेलिजेंसी का सोच रहा हूँ करने के लिए। अभी मैंने इलेक्ट्रिकल कैड सर और पीएलसी स्काडा ऑटोमेशन का पूरा कंप्लीट हो चुका है मेरा।
ओके ओके।
अब देन उसके बाद सर पाइथन C++, क्योंकि सर आर्टिफिशियल इंटेलिजेंसी में वो काम आएगा ना, पाइथन लैंग्वेज वगैरह।
राइट 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 राइट।
यस सर।
So you can apply artificial intelligence to anywhere, to any
Yeah, yeah.
design, to any hardware, to any SCADA or your PLC. anything.
यस सर, बट सर मैं सोच रहा हूँ सर पीजी ये सुप्री में हाइड्रो पावर प्लांट है ना, एनपीटीआई, वहाँ करने की सोच रहा हूँ 1 ईयर सुप्री में।
अच्छा।
यस सर, पीजी। तो सर वो डिप्टी डायरेक्टर जो है ना, मोतीलाल सर है ना एनपीटीआई के, तो सर उनसे कांटेक्ट था सर मेरा, तो वो बोल रहे थे कि बीटेक कंप्लीट करने के बाद आप यहाँ से अपना 1 ईयर पीजी कंप्लीट।
एनपीटीआई कहाँ पर है
सर? ये सुप्री वाला एनपीटीआई।
हाँ, ठीक है ठीक है ठीक है ठीक है, जो नया कॉलेज, जो ट्रेनिंग सेंटर है।
हाँ सर, सुप्री, नागपुर सर, बहुत जगह है ना एनपीटीआई।
राइट राइट, अपने एमपी में है।
तो फिर सर वहां से सोच रहा हूँ पावर प्लांट में ऑपरेशन ऑफ हाइड्रो पावर प्लांट का करने के लिए। अभी सर उनका वर्कशॉप भी है 8 दिनों का, तो उसमें भी रजिस्ट्रेशन कराया मैंने।
ठीक है, ठीक ठीक ठीक।
यस सर,
थैंक यू। आशीष, यू कैन आस्क एनीथिंग। Sri Lakshmi, how were the sessions?
Incidentally, sir, most of the students, they get placed in IT companies.
Yeah, nowadays that is the trend. That is the trend.
TCS, CTS, Infosys,
Right, right.
Wipro, like that.
Because if you see in electronics, we have very limited manufacturing plants.
Yes.
In India, and even fabrication, ICs and foundries, so they are very limited. So most of the EC students also going to the IT and other the software side. That is the thing.
But our EEE is coming up again. Now they are trying to do a lot of newer power plants.
Right.
And they are trying to come out with this concept of smart grid.
Yes, yes, yes.
So there are newer opportunities coming up there. But Bhopal is a very good industrial town. It has a lot of industries.
Yeah.
A lot of industries.
One is near to Bhopal, and one more we have at Indore, and then and Gwalior. Three we have major industrial sectors.
Yeah, I have been to your Indore Institute. What is that famous old institute in Indore?
Yeah, that is GSITS. GSITS.
Yes. Very old, very reputed institute. I went for MBA, sir. I went for MBA there.
Okay.
Very, very good institute.
Right.
And very old institute, right in the heart of the city. But
right, correct, sir. Correct.
Bahut acha tha. It was good and good faculty and very good motivation. They were doing very good job.
Right.
We had given them an A grade, I remember.
Okay. Now our university also we are planning.
Yeah.
To have NBA for 6 departments.
Okay.
So everybody is busy in that, preparing the documents and other things.
Yeah.
So let's see whether we will get.
NAC you have already finished. NAC is already.
Yeah, NAC A grade we have already got. So now we are planning for NBA.
Very good. Wish you all the best.
Thank you, sir. Thank you. So I think you might have heard the news day before yesterday or yesterday. Our Prime Minister has inaugurated a very big solar plant.
Okay.
That is the Asia's biggest, we can say. So that is in our Madhya Pradesh.
That is in Madhya Pradesh.
Madhya Pradesh, yeah. So that power generation capacity will be 750 megawatt.
Oh, Reva.
So it is a biggest in Asia.
Prestige for our MP.
Yes. So from here, they will supply to Madhya Pradesh as well as Delhi Metro. So both will get the supply from the same plant. So that is big achievement for Madhya Pradesh, we can say.
Who has designed this plant? It is that Adani group or?
Yes, sir, I am not aware means, who have done, but 2 days back, our Prime Minister inaugurated that.
Very good. That will give a lot of relief.
Right. So others can also discuss. I think some 15 participants have joined, so they can discuss with sir or anything. They have any doubt?
Ma'am, sir, what's the question? Ma'am, sir, what's the question?
Good morning, sir.
Good morning, sir.
Good morning. Good morning.
Sir, I want to know that what are the applications in the applications of SDR in industries?
Okay, just I will pass your question to Professor. Sir, he is asking what are the various applications of SDR in industries?
Oh yeah, wonderful question. I thought probably at the end of that session we would take it, but anyway, it's good he is asked. First major application now is all the cellular communication areas, all cellular communication. As one of the slides I was explaining, 2G, 2.5G, 3G, 4G. Now in future we'll get 5G. All cellular mobile application SDR concepts will be introduced so that they will be able to switch over from a GSM type of 2G communication to a CDMA type in 2.5G or the WCDMA which they have in 3G or the LTE in 4G. So it's so very versatile. Just by controlling the software, one can change over from one particular generation of communication to the next without sort of interfering with the other systems. That is one of the major applications. The other thing which we see right now is in the field of, on transponder design. You see, the versatility of SDR is that it would use the same hardware. So all we have to do is we reconfigure the hardware through the software to do whatever newer application. And this would be done in a much more accurate way. So that would be the major advantages which come out of this. Also, we look at inter-domain interfaces. So today we have a big problem in changing over from a Wi-Fi system to a cellular system.
Yes, ma'am.
So thanks to this software-defined radio, it will allow us to go over from a cellular, suppose we are in a cellular domain, we can transfer to a Wi-Fi domain.
Yes.
Okay, so this type of interchange and intermodal operation, multi-mode operation, all that gets facilitated very much. Plus the entire range of IEEE services. We have IEEE 802.11b, which is the normal thing which we have been using. From there, it can translate up to the latest one now, which we have. So all that can be facilitated using SDR.
Okay, sir. Thank you.
Does that answer your question?
Yes, sir. Thank you.
Thank you.
Others can also ask or they can discuss.
These are all third year students, sir? Third year or final year students?
Mostly third or final year.
Okay. And then they must be preparing for placement.
And some other faculties also.
They must be preparing for placement also.
Yes,
So
yes.
One or two questions I'm asking them, which will help them for placement.
Okay.
So like yesterday, I was asking them the difference between a connection-oriented network and a connection-less network.
Right, sir, right.
Because the secret of placement is, when we tell the students, is the placement companies always want to find out what they know, right?
So we can start, sir. Okay.
1 minute. I'll just.
Okay, sir.
Yes, sir.
So yesterday we have received many and what presentation he has presented yesterday. So same, most of the participants requested to repeat the same thing. So
Sure.
First we will cover the what yesterday we have done, because yesterday because of the limited time we have moved the slide very fast. So they could not understand and they could not go into deep. So it will be better we can repeat the first one and then today's presentation we can have. So I will start the presentation. Meanwhile, participants can ask or can discuss with the sir anything new or anything doubts or whatever question they have in their minds. Sir, is it visible? I have put the slide.
No, not yet. It has come. It has come, sir.
Okay.
So we'll get into slide mode. Yeah. Very good morning to the participants on the 4th day of this webinar. And we are now discussing the topic on software-defined radio. So what I'm basically trying to present now is more like a precursor, trying to emphasize the concept of SDR. And here we will look at it from a wireless perspective. Okay, go to the first slide, sir. So the major issues in wireless communication is to do with multipath propagation, path loss, radio signal interference, network security, installation issues, and health risks. These are some of the major issues. Next slide. Okay, so now we try to map them into wireless networks for different regions. So we are basically, if you look at the type of distribution which we see on the left side of the slide, which is basically dealing with picocells, microcell, macrocell, and then on the global side, the satellite communication aspect. Whereas on the personal front, we have the personal area network. Okay, so we have the various technologies which are involved in this. First pertains to the personal area networks, which is called the PAN. Then we have the local area networks. Then we have a typical example of the local area network is what you have in your laboratory, in your computer laboratory when you're doing the networking experiment. You would have noticed that about 30 to 40 computers are all connected to a server through a cable system. Okay. Then we have the metropolitan area networks. We will try to define the region to which that coverage takes place. And of course, the wide area network, which we are talking, where figuratively on the picture, which we can see the satellite network there. Next slide. Yes. So immediately now we tend to classify this. So we are classified into 3 different categories, mainly personal area network, the local area network, and the metropolitan area network. So if you look at it on the fixed wireless personal area network pertaining to Bluetooth and UWB, both these technologies we had discussed in our application on the first 2 days quite extensively. And generally the area of coverage is restricted. Normally the Bluetooth can go up to 100 meters and UWB is restricted to 10 meters, but it can be escalated if required to 50 and 100 meters depending on the application. Okay. Then we have on the metropolitan area network, on the fixed wireless, we have the cordless, the wireless in local loop. This was a technology which was there for some time back, nearly 20 years back, and first time it came in, but then now it has been abandoned for more popular networks. On the LAN technology, we have the local area network, which is basically running through a family of 5 to 6 of them, but it generally gets the designation of IEEE 802.11x. 2 popular ones are the B11B and A standards. And then, of course, we have the G standard also coming in. Then a separate hyperLAN is also there, which is working typically around that 54 megabits bit rates. Then on the cellular side, which is basically having the metropolitan area coverage, we have going from 1G to 4G. So on this, these are the areas where the SDR has excellent applications. Then again, on point-to-point and point-to-multipoint, we have the LMDS and MMDS and the IEEE 802.16, which is basically the WiMAX area. And lastly, on the mobile SATCOM, we have the wide area coverage network. Next slide. Yes. So I wanted your attention on this very important slide, which is basically the configuration of a transceiver of a wireless system. So as you go from left-hand side to the right-hand side, on the top blocks, we see the source code, the source coder, the channel coder, then we have the interleaver, the modulator, analog to digital conversion, then you have the mixer, and naturally the local oscillator coming from a frequency synthesized source to maintain the frequencies very accurately. Then, of course, the transmitter associated with the transmitter is the amplifier. That is basically the power amplifier before it goes to the antenna. Then, similarly, on the receive channel, you have what you have shown below here. And right below, we have the blocks which are represented in blue, basically using DSP and microcontrollers, we are able to configure them. and we have using the yellow blocks, which are basically digital ASICs. We are able to configure the yellow blocks and then the analog and mixed signal processing ones which are there. So what I want to draw your attention to when you look at this block diagram, we have to answer a very important question a little later. Out of these blocks, which of them can be converted to software, right? So the essence of software-defined radio is it takes a hardware which is already available in the radio transmission blocks. And from that, we tend to convert that to software. Which of those blocks can be converted? There are certain blocks which cannot be converted, which have to be kept back in the hardware portion, especially the antenna and the RF front end. These are areas because without the antenna and the RF front end, you will not be able to receive the signal. There's no point having software if you are not able to receive the signals. So they become a little indispensable, these hardware, the radio receiver front ends. So we'll see more of it in the subsequent slides. Next slide, please. So on the advances in communication systems, we see those are what we had seen in the previous block, how we do the implementation, source coding, modulation, multiple access methods. These are all the modern communication techniques. Then we have channel coding, and immediately to the students who are appearing for campus interviews, one very popular questions with the students, for the students is, what is the difference between source coding and channel coding? Very, very popular questions they have. So please look it up. And anyway, you're studying about it, you could see how they are manifesting here. Then we have the diversity methods and MIMO, equalization, and the analysis, especially the capacity of feeding. And then we have the important enablement is the IP-enabled services and convergence, and voice in multimedia over IP, a very important area for all of you to digress is IMS, which is called IP-based multimedia services, and diversity methods, and MIMO, multiple input, multiple output, which is being exploited in a massive MIMO fashion, especially for 5G communication, also being used in 4G. And then, of course, advances in the VLSI, DSP, and SDR domain. Next slide. So on the advances in wireless, these are some of the areas which already you're familiar, especially UWB, wireless sensor networks, RF tags, WLAN, next generation cellular. Then we come to what we are going to exploit in a big way is basically system on a chip technology and system on a chip, IP-centric technologies and convergence. And then we have come to software-defined radio, which is coming in as an advancement in wireless technology. Next slide. Next slide, sir. Yes. So again, I want to draw the attention of students to this slide because it basically tells you about the evolution of the digital cellular standards. And why I'm trying to draw your attention here, it is in this type of domain where we find SDR applications coming in a big way. As one of the students was asking, where would be the major application of SDR? You will find SDR coming, already operating in a big way in this. And tomorrow we will have a detailed explanation of how this has been exploited in the WANU way, VANU. We'll talk about it tomorrow in a big way. WANU application, okay? And I would like all of you to go to Google today and type WANU, VANU. WANU communication has been started by those of you who are familiar with Bose speakers, BOSE. They are high fidelity speakers which we use in the music domain. So his son has started this WANU communications, and today he has exploited this SDR in a big way. So a lot of newer application is coming from WANO communications. So I'll be discussing that aspect tomorrow exhaustively. So coming back here, when you look at the first system, the GSM system, global system for mobile communication, which was also called Group Special Mobile, which is a European standard. It started with 2G, and the killer application for 2G system was what you see below, basically SMS, that is texting at a speed of 9.6 kilobits, very modest speed, because 2G digital communication was basically voice-centric and it was not data-centric. But then it had this nice feature where one of the big application today, we say it's a killer application for 2G, is it is being utilized very well using the SMS, let us say for our election purposes, a lot of propaganda they are doing. We have application where fishing farmers are able to use the GSM phones, and they are using it in a very innovative fashion. And what is important is, thanks to the development of natural language processing, NLP, today everything has been translated to local languages. So if you go to Indore, if you go to your Madhya Pradesh, you will have SMS in your local language available. So the fishermen of Kerala coast use this GSM phone using SMS, 3 SMS in Malayalam. They send it to station A, B, C. Station A, they take in the fishing trawler, which is basically they've gone into the sea for about from night 11 p.m. to morning 4 a.m. They've caught about 25 tons of fish, and they use 3 SMS. First goes to station A, which sells the fish at 10,000 rupees per ton. Station B says it is 15,000. Station C says it is 18,000. All that they get in their own SMS Malayalam language. So straight away he takes the mechanized boat to station C, and just within 1 SMS he's made a profit of 8,000 rupees per ton. So you see how ingeniously they have used. So similarly, the vegetable vendor or any other type of application, you students can think of newer application. So that is why this is sustained 2G communications. Then we go to 2.5G, which is GPRS. I was telling you about a nice application yesterday. So where the data rates have got translated and it has gone up to 150 kbps. So these two are examples of circuit switched systems. And then from there, we have, and the moment you enter GPRS, we go to packet switching, and 3G is all about packet switching, where you have Edge and WCDMA. 4G is also, so there onwards it is packet switching. Only the initial 2G and some aspects of 2.5G are in circuit switching space. Similarly, the North Americans, in America, we have the standard of IS-95, and then we have 2.5G here. Then we have 3G, which was basically in the CDMA type of operations. So what is important is, in India, we have a good mixture in which we not only took the European system, but subsequently we took up this CDMA 2000 and 3X CDMA system before we translated to WCDMA. So in India, we had both. The CDMA 2000, basically the country which has done a lot of good work in that area has been South Korea. In South Korea, this has got exploited in a big way. That's why they were able to get into 4G very easily, and now they are also into 5G. Okay, so India has got a good mix of both these European standards as well as the CDMA. But very importantly is the big problem which you find is with all this, with that normal phone, we cannot have roaming. That means we cannot use a GSM phone and go to a foreign country like USA and say this will work. So one of the first things they have done is that they have standardized, and they wanted a single communication system by which they can have free roaming, improved QoS, enhanced features, and international roaming made possible. That's why when they went to 4G, now of course going to 5G, they have single good world standard. And these are some of the very important contributions which are being made here. Okay, next. These are typical hardware on which a lot of these things can reside on, and showing typically where all you can implement this. Because we'll be talking on the Nokia 3G thing in some more detail. Next slide, please. Next slide. Yes. So I want to draw your attention to this. It is called system on chip. So what is basically sitting inside your cell phone, okay? So if you look at it very carefully, you will find there's a combination of RF ASICs, then you have provision for data conversion, then you have baseband processors using digital ASICs, then you have the source coding being provided by digital signal processing, and then you have microprocessors and microcontrollers, which are basically taking care of protocol processing and system controlling. So all this is manifested inside system on a chip. So if you look at it, you look at these 4 blocks with which this whole thing is being done. So tomorrow, subsequent slides, when you look at it, we would basically, now we are interested how to integrate all these blocks together and facilitate trying to put all this into a single chip is where we are trying to now further type of integration is being looked at and how this is getting implemented. Next slide. Yeah, this is the VLSI technology roadmap, and you could see how the type of advancements are made from 99 to about 2008. Because we are still behind another 10 years, but there have been still improvements, and you could see the millions of transistors which they are able to put on the chip, where now it has got translated, and the process technology across chip clock speeds and the wiring levels. Next. Next slide, sir. Yeah, this is basically just to get an idea about the rate receiver chip, which is used in a lot of your CDMA application for UMTS. So you could see in what a small area they pushed in all this, the supply and the type of configuration in which they have been able to put all these transistors together, and they also like to see how that mapping takes place. Go to the next slide. Next slide, please. Yes. So we have now system on a chip. So what is very important is we have evolved from ASICs into system on chip, and the use of pre-designed IP blocks, the technology for future system, the RF CMOS technology, which is of low cost. And here we have high performance and low power chips for portable applications. So we've taken a PDA, personal digital assistant, and this is what it basically consists of: the RF, the baseband, network protocol processing, and the memory, which is available on system on chip. And you could say typically the operations are from 300 million operations to 2,500 million operations, which are being made available in this whole system. Next slide. Yeah. So now we are getting into the software-defined radio. This was basically the Nokia model, which you have seen. So what we are trying to say is there is a software library of communication subsystems which are available, and using our access, the open source access, we are able to download that software, and then we can configure depending on the requirement. But the biggest catch here is that software which we download and try to put into our system, will it be virus free? Will it be free of all the major problems? So one has to necessarily evaluate that software. So that is where we have to be very careful before we introduce this software into the radio. So what it does is now this particular system lets users enable, reconfigure and upgrade a single device to support multiple functions and protocols, permits use of a single device in a variety of ways in different radio environments, and perform intelligent networking and other advanced functions. So what is important is we are able to use the same radio for different applications. So you could use it for this IEEE 802.11b, that is basically the wireless LAN type of application. Then we can go to CDMA, that is the 2.5G standard or the US standard. Then of course for GPS type of application, which can also see UMTS, and then we have GSM, okay, and Bluetooth. And lastly, it can perform intelligent networking and other advanced functions. Next slide. Next slide, please.
This is the one or next one, sir?
Next one. Yeah, this is the one. So libraries of different standards. You have for RF, IF, modulation, coding, access, and it provides features that are useful for intelligence gathering, and other tasks. Okay. Next. Next slide. Yeah. So the major research issues are new energy efficient algorithms, okay, reconfigurable architectures based on ASICs, digital signal processing for SDRs, field programmable gate arrays for SDR silicon. So these are major research areas in which SDRs are being configured, and also a lot of research inputs have got, and they have evolved from there. Next slide. So the capacity enhancement and enabling techniques. So in that we have multi-user detection, we have an antenna array, transmit diversity, transmission power control, turbo codes, software radio, high performance DSP, high energy rechargeable batteries. So these are all on the capacity enhancement requirements. Next slide. So if you look at the trends in wireless communication, and what you see at the bottom is the low data rates with which it was basically thought about. Like our SMS application for 2G is about 9.6 kbps, which is a very low data rate that cannot handle. That's the reason why they translated to other generation systems, which can be brought. But you could see what are the type of speeds at which they are able to function here. And when we go to WLAN, which basically operates in the unlicensed band of 2.45 and 5 gigahertz, we have the data rates translating from 2 megabits to 11 megabits to about 54 megabits. Okay, whereas next generation wireless LANs have gone up to 100 megabits. Okay, so that is one. And then on the 2G side, which you see on the left side, from 9.6 went to 28.6, and then typical frequency of operation is around that 900, 800 megahertz up to about 1.5 gigahertz on the 2G. And then 3G is basically operating at 2 gigahertz, IMT 2000. It starts with 384 kilobytes and goes up to 2 megabits. So you can see how the broadband and seamless transmission is what they are able to achieve. So what is important here is target data rates of 100 megabits for high mobility and up to 1 gigabit for low mobility is what they are able to see, and greater flexibility to support many different types of services simultaneously. This is one more ability which SDR can really harness. Next slide, please. So on the cellular thing, we have 3.5G. So this is basically this HSPA denotes high-speed downlink packet access, which is basically evolved from 3G WCDMA, and transmission speed is up to 14 megabits, even when using same 500 megahertz bandwidth as WCDMA. And this service got started in mid of 2000 to 2010, about 2006. And the moment you go to 4G, we are able to go to still higher speeds, starting from 100 megabits, and a good speed like 1 gigabit is where, using MIMO technology, is where LTE is getting experimented. Next slide. Yes. So these are the trends in which IEEE 802.11 WLAN has been progressing. A very popular slide. I want all our students to concentrate on this slide, especially when you go for campus interviews. There are very many of them ask you questions on this. That means what we start with 802.11, which was a good example of direct sequence spread spectrum. Okay, and it also was exploiting the infrared. Somebody was asking, infrared communication is also being used in this type of local area network. But moment we went to 11B, okay, direct sequence spread spectrum, 11B, that was 11A is frequency hopping, okay. So from here, 11B is, they're using this. So that speed, 11B, is typically of the order of, the normal 802.11 speed is 2 megabits, 11B is 11 megabits. So the moment you go to 11G, it has picked up the speed to 54 megabits. And then 11A, which is on a different footing. What is important is 11B is not backward compatible with 11A, but 11G is backward compatible with 11A and 11B. Okay, so this part one should remember very carefully. Similarly, from 11G we go up to now the standard of 11N, which is talking about speeds like 100 megabits, which you are able to get. Okay, and these are typically how the years in which they evolved. So today we have, thanks to SDR, we can configure from a cellular system to any of these systems using appropriate software. Next slide. This is on the fixed wireless access, and some of these requirements on fixed broadband, a lot of these applications are being done, and you could see typically the type of data rates and applications they're doing. Next slide. Yeah, more details about the wireless terminal and examples of service. This is basically in Japan. where they have been implementing this. Okay. And typically the type of access points and coverage which is being given. Next slide, please. Yeah. So this was another standard which also came in a big way, 802.16 WiMAX. So you will find two standards which have been competing very closely. One was the LTE standard, and the other is this WiMAX standard. Okay. So they have come with two different requirements, and ultimately we find LTE now sustaining on the cellular side. Next slide. So now we come to essence of beyond 3G. So what is it? We find what is the biggest takeoff. Different radio access systems will be connected via flexible core networks. Individual users can be connected via a variety of different access systems to whatever networks and services it desires. So the key requirements will include interworkings between different access. That means we have this vertical handover and horizontal handover and seamless service provision. So to summarize that, we have come out with where SDR can be very well exploited is for multi-mode, multi-band infrastructure and terminals. When you're going from one mode to the other, software-defined radio is a very strong possibility which can embrace multi-mode and multi-band infrastructure operation. Next slide. Next slide. Yes. Again, let me draw your attention to this block. Of course, on the further slides, we'll be studying it also. But again, that very important question. Which of them, that is, first of all, we try to define what is an SDR? What exactly is a software-defined radio? A reconfigurable radio equipment whose function can be added or modified just by changing the software. It means we will keep the hardware as it is and change the software and configure it for different purposes. Let me give an example. We want to use it for 2G communication, global system for mobile communication. So we will introduce the software pertaining to that. Now we want to change it to 2.5G, which is a CDMA type of requirement. So we will change those blocks which are required, and it can get configured for 2.5G. Similarly, we go for CDMA, wideband CDMA for 3G. So we will again change that portion of the software pertaining to that. But what is very important for us to remember is when after finishing that, there are common parts which are associated with RF and antenna. So the important question is which of the portions in these blocks are programmable, which of them are not programmable. So if you look at it carefully, you will find the RF and the antenna portion have to remain in hardware, whereas the rest of it, the digital processing blocks, which are basically with A to D, D to A, programmable processors, external IF controller. Okay, these are basically, we are able to get software which has been developed by a lot of companies, organizations, which are kept on a common, maybe on a cloud platform or whatever type of platform, from where we can download via storage media and then push it into those particular blocks to configure it the way we want. Okay? So this is based on independent variable like frequency, the type of air interface which we want, and the type of service which we want. Okay, so of course, a little later we will discuss some of the limitations which are there and to what extent can these operations take place and how comfortable are we while trying to take it. But the important definition here is if you look at the radio receiver, right now the radio hardware blocks which were there earlier, now we have been able to simplify what was totally in the hardware domain. We have shifted many of them to the software domain, but there are 2-3 blocks which are indispensable, where necessarily without an antenna and RF front end, you will not be able to receive the input signal, however sophisticated is your software down below in the subsequent sections. Next slide. Yes. So on this, on a different note, I bring in this slide basically because today we look at the service engineer, especially those of us who have been associated with the electronics laboratory, electronics and communication laboratory in our colleges. We always used to have a service engineer who used to come with a box, service box, carrying all the tools, which you see the gentleman on the left-hand side. Okay. This was the older way, where you had all the contrivances, like right from screwdriver to tester and all that modules with bringing a board or chips or whatever type of things. That means now we have what we have on the right side is the new service engineer. What does he do? One terminal he brings, and he has got licensed software downloaded. And because when he comes to service that particular radio, which is to be configured, he has all details about that already provided to him. So what happens is one terminal can be used by various wireless systems. That is, whether it is cellular, WLAN, WPAN, MAN, PAN, TVITS. With this type of ubiquitous access using one terminal, is able to download all the software. So new services can be provided or obtained by software version upgrade without replacing infrastructure and terminals. Bug fixing over the air download. In-service systems can be remotely maintained. No longer need to develop specific chips for each system. So you could see how much the simplification has occurred, especially in the service domain, because it is not sufficient for us to acquire new system, but we should be able to service it as and when the require comes. So, so you can easily replace due to the new models or recalls, which I was doing earlier. Now you can go to the field and get it done. No need to transport the system from 100 kilometers away or whatever it is. So it has simplified a lot of our service requirements. Next slide, please. Next slide, please. Yeah, this is a service view. What it says is seamless communication made possible by selecting the wireless system best corresponds to the communication environment and user requirements. And you can maintain your desired QoS, quality of service, while improving service economy based on data rate. And depending on which domain you are, okay, and which type of service area you want to access. Okay. And in the office premises or the home premises or a public service area, you can configure this depending on the type of service which you require. So it caters to, in a seamless way, to different service requirements. Next slide. And the important feature is it has got the over-the-air down. This is a little bit of the SDR development. We can skip this slide, not a problem. Potential issues to overcome here, okay, is programmability for functionality in multi-band RF circuits. So here we have to deal with system architecture, software architecture, programmable processors, multi-band RF circuits, multi-band antennas, and the framework and network has to have technical regulation conformity, integrity verification of downloaded software, roaming and handover between heterogeneous systems. So what is important is how can we provide flexible, efficient, and secure function changes? And how can we build networks to support seamless communication service? That is important. It's not sufficient you have sophisticated system, but you must have a seamless way in which that can be serviced. Next one. This is basically regarding NTT activities. Okay, Japan. It's okay, we can skip this slide, no problem. Yes. Again, I'd like to draw your attention. This was what happened in 2001. Okay. And here you can see a very good view of what are the areas in which we can take up. This is that SDR prototype which was first developed. So you could see the various blocks which are here. And what is important for us is which of these blocks are reconfigurable for us. Okay, that means moment we are able to do that, we can use the same hardware and load this software. Okay, so as you see the front end, which is basically operating on these frequency of 1.5, 1.9, 2.45, that is basically the cellular Wi-Fi as well as the WLAN band frequencies. Then you have the multi-band RF, which is the filter switching type, the RF side, and then the fast ADC, analog to digital converter DAC. So you will find all that in pink, which is indicated here, are all the reconfigurable ones here. And we have the source coding and all that being done by DSP here, the CPU and OS and ADC, in which some of these major device requirements can be put here. The system control, and especially for WLAN as well as PHS systems, can be taken out, and depending on what type of requirements are put across. Okay, next slide. Processor issues for mobile terminals. Okay, these are some of the requirements and what is the approach they normally try to get. That means we look at for miniaturized hardware, low power consumption, high speed signal processing, to develop a IEEE 2.11a wireless LAN baseband using appropriate reconfigurable processor for the SDR mobile terminal. So this is the approach in which it is done. Next. Next slide, sir. And we have a little bit of configuration, how it is being done. Dynamic reconfiguration using FPGA or DSP here, high-speed signal processing. We expect reconfigurable processors to be suitable for SDR mobile terminals. Next slide. Yeah, we can skip this. We'll go to the next slide. Yeah, so these are some of the major processor issues. The prototype processor was not optimized, necessitating slightly improvements, and showed potential of reconfigurable process for application to SDR mobile terminals. So we are able to exploit the SDR for a lot of these type of applications. Next. Then we have security issues for SDR in conventional radios, what it is. Okay. So in SDR, we are able to change function by changing the software. New problems which arise with use of SDR, that is something which have to be reckoned. That means new technical regulation, conformity, certification rules, new security measures are needed because we are downloading a software and putting it into a new system. So both the licensed software permission should be there, as well as error-free or virus-free software should be enabled. Next slide. problems raised with illegal software, which you find here, the radio law here, method of illegal, damage, copyright, and criminal law. These are some of the problems faced. Next slide. Okay, some more security issues which are there on distribution model. On the attack side, you could see what is happening here on the right side, and security architecture. So we will find security layer 3, we need data protection, privacy protection for the user. On security layer 2, right protection. Security layer 1, regulatory issues, government and certification agent. So this is basically the security architecture for SDR. This has to be conformed with, especially on the SDR software distribution model. They have to necessarily have all this architecture in place. Then only they can issue that software. Next slide. So now this is a study group on software technology for radio equipment and discussed effective methods. So the biggest objective in SDR is to build an architecture which allows users to install software exclusively in combination of hardware and software that have passed the certification test. Propose new idea using tallies. So an example of a method giving tallies to hardware and software check system using certification matrix. So today, what is the very important thing which they are doing is they are using a combination of hardware, software together, in which they are able to implement this security issues. So there is another important area, a lot of research is being done. These are FCC rule amendment. We'll skip this, no problem. Go to the next slide. This is the SDR forum, which was established, and what is the charter and what are their requirements. Okay. Next slide. This is the strategy.
सर अंकल बाहर चले इनवाइट कर
लगता है सर का कनेक्शन डिस्कनेक्ट हो गया है। Sir, please unmute yourself. Voice is not coming.
Unmute. I have to unmute. Yeah, now can you hear, sir?
Yes, yes.
It's okay now?
No, yes,
Yeah.
it is okay.
Yeah. Now go to the next thing, sir. Next slide.
So this is the one, cognitive radio or next one?
Next one. Yeah, I think we have come to the end of this.
Okay, okay.
And we can now go to the next presentation. If students have any questions when you're putting it up, we can address that.
Yes, yes, yes.
Okay.
So I am putting the second presentation. Meanwhile, participants can ask doubts or
Participants can ask any questions.
yeah. They can unmute themselves and then they can have the discussion.
Yes. Fine. That's the first slide. Yeah. We can go into get to the first slide, sir.
Okay.
Go to the next slide, sir.
Sir, this is PDF, so
The PPT slides are not there, sir.
many participants know how to run PDF in a slide mode.
Yes, sir.
Oh, sir, this is PDF actually. So,
No. This particular thing is a PPT. Next one only will be PDF.
no, this also, sir. This also PDF.
PDF. Okay. Then can you proceed to the next?
Just a minute. Just a minute, sir.
Okay. Fine. Okay.
So I have to do something else. So we keep on doing. Okay, no problem.
So this is the outline, how it is. Okay, let's go to next slide.
Okay, sir.
So again, we are reiterating and doing this. The definition here, very nice definition which is available. It is a technology wherein software modules running on a generic hardware platform. Watch this word, generic hardware platform, consisting of DSPs and general purpose microprocessors are used to implement radio functions. I repeat, it is a technology wherein software modules running on a generic hardware platform consisting of DSPs and general purpose microprocessors are used to implement radio functions. So this then is the definition of SDR from what background we have learned, and you can see this is sort of reiterating that point also. Next slide.
Sir, I will open in the PDF. Just a minute. Just a minute.
Yeah.
Sir, is it visible?
It's not visible. It's not going. Now it is coming. It has come. Next. We'll quickly run through this. Yeah, next. Now it's coming. Yeah. So now this slide, let them have a look at it. What does it do? We could produce a radio which can receive and transmit a new form of radio protocol just by running a new software. Okay. And this technique in which all the processing is done in software, that is, what are all the processing which is taking place here, is basically do with mixing, filtering, demodulation. Of course, more on the PPT slides, which I'll show later, and used to implement different demodulation schemes, and different standards can be implemented in the same device, can be updated so that the device doesn't become obsolete with time. Okay. So normally what happens is, if you have this hardware after 10 years, to get the new system, we have to throw it off. Here, we can use the same hardware, generic hardware, load this software, retain it. Next slide. Yeah. So the important question, this is again, I want the students' attention. If software does everything, what is the role of hardware? Okay. So please remember, the hardware is still needed. As I told you earlier, when we saw all those examples, RF front end, ADC, D2A, as well as the antenna portion, all have to be necessarily in hardware. Without that hardware, you will not be able to get into accessing the software which you have implemented. Next. This is again a very big reiterating point. Yeah, the basic radio receiver point, which we have taken these frequencies for an example. Okay, and you could see this is basically a system where we have the antenna, the filter, the mixer, oscillator, and then the IF coming here, amplifier, demodulator. Basic radio receiver unit. Let's see how it is in the SDR version. Next. So on the SDR architecture, you see how the mapping takes place. This is where, that's why I put these blocks, so that students will get an idea how exactly is the mapping which takes place between a normal radio receiver and one which we are developed in software. Software, that means you have the antenna and then the RF, IF, which are basically the flexible RF hardware which is there. This module you have to necessarily have. Then we have the ADC. ADC, again, we'll talk about this in more details here. And then we have the digital front end. From here onwards, we find basically all the software areas coming in, the channelization, sample rate, all the digital front end is where we can do it. All the processing, okay, which we do, especially the baseband processing, is all we are able to do using this software, which we can introduce into this architecture. Next. Okay, this is the typical hardware cost, how it is. And these are the ideas with which you get. The students can look up. You must see what is available in India right now, of course, on this. Next slide. Software. This is a very popular GNU radio software, okay, which is the one on open source, which has been brought in a big way. And on Windows, we have SDR and HDSDR, Spectrum Viewer, because both have come now with this background here. So we have Windows, Mac, and Linux cross platforms on which all these things can be got. Next slide. On Android also, we have these things coming in now. Mac and Linux are this. Next. So the software communication architecture, what does it do? It provides a real-time software operating system environment to support the dynamic waveform generation and signal processing aspects of the radio requirement, as well as the administrative aspects for radio installation and change control. Example of standardized architecture of hardware software will lead to generic flexible radio systems which can be loaded with application to suit particular operating scenarios. So SDR can be flexible enough to operate in several modes at the same time, and some may be capable of changing or adding modes while continuing operation in other mode. So they have different capabilities. Next slide. So the communication interface with SDR, how it is being done, is illustrated here. Okay, from the device manager, we have the sound card executable device, FPGA modem, and then we have all these type of things coming in here, and you could see the architecture with which this is being done with the interface. Okay, we can study it leisurely based on that. Next. So, of course, all our software people will be very familiar with this, the CORBA type of architecture, which is basically acronym for Common Object Request Broker Architecture, that provides infrastructure for computer applications to work together over a network. Okay, and many of them can be exploited instead of doing a customized type of software development. Next. So this is again the blocks which are all coming into this requirements to enable this type of a thing. You could see programmable hardware, OS and middleware, core framework, the applications, and where all of them are coming together. Next. And then the GNU radio software, which is basically on the open source platform. Once it is developed, how this whole thing, the type of waveforms it produces, just to give a snapshot of it. Next. And we have taken the example of FM demodulation example in the GNU radio and how this whole thing is implemented. You can leisurely go through it because we are going a little fast here because we have to look at 2 more presentations. Next. Yeah, this is a Python auto-generated code. Now you could do it in C++ or in C also, but those of you who are familiar can look at it. Next. So various applications we find in public safety, cell phone technology, military application, and commercial use of SDR. These are some of the very important areas where SDR has taken shape. Somebody was asking various applications, so you could see where they are coming in. Next. And major benefits you could see are put out here. Next. So these are some of the disadvantages which you see here, because you must look at the negative side of it also. And we find this is important. The last one, software reliability may define the overall radio reliability rather than hardware limitation. Okay. So earlier we were limited by the hardware. Okay. But now we have brought in software, so it has to have the required scalability and security as well as reliability. Okay, fine. Next one. So future scope is in this area of adaptive radio and a little bit of cognitive radio, which we'll be taking up tomorrow. Right? So that is the Venn diagram which gives you. Fine. I think we can go to the next slide, sir. Yeah. So now with this, I will go to the presentation. I have marked it as Subramaniam. That is our first paper on front end. Okay. That's again a PDF file. So
yeah, I will put on that.
Yes, sir. So if there are any questions, I think we can answer.
Some more water is available. Here you can. So that's setup.
Not this, this is the second presentation. Okay, the previous one, but this is the one which I'll be using. I thought, okay, we'll use this, no problem. Okay, so, yeah. Can we make this a little bigger, sir? Can we expand? Yes, correct. Fine. This is good. So now we come to the first of the presentation, what it does is, this is the research paper which got published in the IEEE International Conference in 2009, Wireless Vitae, which was incidentally held in India at that time. And that was the time when this was the title, Front-End Design of Software-Defined BTS, Base Transceiver System for interoperability between GSM and CDMA. As you know, GSM is the 2G type of communication. CDMA is something which was prevalent in the US system. So these are two different systems. So we are trying to show how by using the software, we are able to interface between these two varied systems. So as the title indicates here, and here we see that software-defined radio, what does it do? It aims at using the same hardware for different applications just by change in software parameters. Okay. So as it reiterates this, the reconfigurable part in SDR is the digital front end, and the parameters which can be modified for different standards include bandwidth, sampling frequency, down converted to IF, up converted to IF, filter cutoff frequencies. One question here which I would like to answer, why is it that we want to bring RF to IF? Okay, and then of course we are looking at baseband. This is basically because if you are working at RF, the ADCs are unable to work at that very fast data rates. Okay, it will be very, very difficult for us to conceive that data rates. Okay, so that is one. And here now the major goal for ideal software defined is to replace ADC as close to the antenna as possible, so that moment we receive, we are able to translate that quickly into our baseband requirements, and then we can take up all the other functionalities. That means, how do we achieve this? Using bandpass sampling, automatic modulation identification, which can be used in conjunction with the design principles of SDR to make the transceiver more flexible. Okay, so this research paper addresses the design of RF front end and software-defined base transceiver station, which can be configured to support different technologies. Right. So then, if you look at it from ADC, what happens? Okay, but before I get to that, can we push this up a little bit, sir? Move it front. Yeah. Yeah, I think. So so what we are basically doing here is, so it uses this, the main aim of the SDR is to design the reconfigurable hardware which can support different technologies here, and you have taken BTS here, application which can support GSM, Global System for Mobile Communication, and CDMA, Code Division Multiple Access, which is on IS-95. Okay, so SDR uses the programmable digital device to perform signal processing necessary to transmit. Okay, and let us take an example of this typical digital system architecture. And you could see that it consists of the digital subsystem and a simple analog subsystem. Okay, and a typical SDR architecture here, we find in under Figure 2 the digital front end of the SDR, which is coming from digital to analog conversion, and here from the source from the source coding, from the DSP, we go to the modulator, then we have the FIR filter, because we use the I and Q channels and do the up conversion. So here we have this block called NCO, which is basically called the numerical control oscillator. That is the one which replaces the local oscillator in our normal super heterodyne receiver or the normal radio channel receivers. Okay, so with that we can use that to do the up conversion, and then from there using the DAC module to go into the antenna system here for radiation. Okay, so the important aspects here we should remember is that devices such as DSPs and field programmable gate arrays use the software to provide them with the required signal processing functionality, and this technology is able to offer greater flexibility and potentially longer product life, since radio can be upgraded very cost effectively with software. Okay, and typical SDR architecture would consist of this digital subsystem and the simple analog system antenna with RF filtering. Okay, and here in figure 2 we see the ADC in SDR converts the incoming signal to a particular IF, and the frequency of the NCO can be varied to bring the down converted IF to baseband depending upon the incoming signal, and FIR filters are reconfigured accordingly. Sir, we can go to the next slide. Next page. Yeah. So here we have a first module which takes care of the automatic modulation identification. So this AMI is the one which distinguish between the modulation schemes, whether it is a GSM scheme or a CDMA scheme, and it basically differentiates between the modulation scheme we use in GSM is the Gaussian minimum shift keying, and the other CDMA uses quadrature phase shift keying. So AMI is used for at the front end of the SDR receiver in identifying the incoming signal. So after it identifies the incoming signal, the receiver architecture is configured correspondingly. So from there we can use the transformation, and the GMSK and QPSK modulation is processed in the following scheme: that we make use of a hard transform of the modulated waveforms first performed, and the detailed approximate coefficients are obtained from the hard transform. The extracted coefficients are plotted on the histogram and computed for the detailed wavelength. Okay, the histogram is computed. So we'll go up now. We'll go up. We'll still go up. Yeah. So this is the histogram of the GMSK signal. Okay, and computer simulation is done here. And then you can come down here. Next one. Please come down. Little bit. You come down. Yeah. So what happens is, most radio application required sampling rate for ADC would be impractically high if Nyquist sampling is employed. So GSM 900 digital cellular telecom, this is a very important point. So if you're operating at 900, the sampling frequency has to be at 1.8 gigahertz. So such a high sampling rate is infeasible with the present technology. So alternatively, what we do is, by the bandpass nature of the radio signal, we use a bandpass sampling to directly down convert the desired RF to an IF. So that is the technique which we follow and with which we are able to process this. So that is how we are able to do the down conversion. And this is the histogram of the QPSK signal. So examining these two signals very clearly, we can distinguish between a GMSK and a QPSK. GMSK stands for GSM, QPSK stands for CDMA. That is how the segregation and configuration is done. Okay. So next, we go to the next slide, next page. Go to the next page. Yeah. So here we have table 1, in which the range of valid sampling frequencies for 2-band case. We have chosen 2 frequencies. As I told you earlier, GSM band works typically from 890 megahertz to 960 megahertz. So here we have chosen 2 channels. One is from 890 to 890.2 megahertz. The other is from 900 to 900.2 megahertz. And IS95A, which is a CDMA system, operates in the 800 megahertz band. That is from 824 to 825.25 megahertz and 840 to 841. And associated, the sampling frequencies which have been chosen are the values which are shown here. So what happens is the 2 RF signals of different standards, basically GSM 900 and IS95A, which is a CDMA standard, are taken. And for a given set of bands, many possible values of valid sampling frequency ranges, some of which are shown here. From the range of sampling frequencies, a particular value is chosen as the sampling frequency. Also, the value is down converted IF are obtained through the equation above. And values are shown in table 2. Can you go up, please? Can you just go up? Table 2. Please go up. Please go up. Please go up. Yeah. So in table 2, sampling frequency is chosen and the value is down converted IF. So for a sampling frequency of 0.8165 megahertz, IF was 10,590, and IF2 is 30.307082. So these are how the IFs have been chosen. The same concept can be extended to N-band case. Okay, so the N-band algorithm can be obtained by using repetitive process of finding the ranges of sampling frequencies by considering 2 bands at a time. On the valid ranges of the sampling frequency obtained, any one value can be taken, used in the receiver architecture. So these are plotted in table 2. Can we go up again? Please go up. Table 3. You have to go to table 3. Table 3. Still up? Yeah. So in table 3, what we have found is we got the standard, we got the channel range, we got the sampling frequency. For GSM 900, you find the channel range is from 890 to 890.2, 891.2 to 891.4, and this is the range. And IS95A, the CDMA system, this is the range. These are the sampling frequencies which have been chosen. So the same procedure is then followed and sampling frequencies chosen and the corresponding IFs obtained are tabulated in table 4. Now go up. In table 4, we can see the sampling frequency chosen and the values which have been down converted. Still go up. Little bit you go up. Yeah. So what we find is for the sampling frequency from 1.811 megahertz to about 47.94, we find IF1 in hertz. Okay, we have this type of representation, IF2 and IF3. So these are the ranges. Okay, so we have found out sampling frequency chosen and the values of down converted IF. Okay, so with this background now, having evaluated the various sampling frequencies and the appropriate IF, we can now fit this into the SDR architecture. Go to the next page, please. So this is the SDR receiver architecture. You could see the Gaussian noise generator and IS95 split band here, the GSM band here, and the ADC the low pass filter, and numerical control oscillator is, and we have segregated into 2 channels here. Okay, precoder product for product 1, product 2 under GSM, similarly for product 3 and 4 under CDMA. So this is how the overall architecture, receiver architecture has been configured. Next. You can still go up on this page. Yeah, still go up on this page. Yeah. So what happens is now, so with that background, we find for GSM, we have 890 to 890.2 megahertz for GSM and 824 megahertz to 825.25 megahertz for CDM. The sum of these 2 bands is considered to be the received signal for the BTS. This signal is then sampled by the ADC, whose sampling frequency is determined by the algorithm. Okay, luckily. So we don't get into that RF sampling rates of 1.8 gigahertz, which becomes very difficult for the ADC. So there are many possible sampling frequency. One of them which we have chosen is 21.19 and 21.97. And choosing this as the sampling frequency of ADC, the incoming signal is digitized and down converted to IF. And so we find the spectrum of the simulated GSM and CDMA, things which you can see practically available in frequency on gigahertz. This is CDMA, you could see here, GSM you can see, because these are the 2 frequencies which we have brought inside, because they have to, through software-defined radio, we want to have a working for both the systems. Now we go up again, we'll go up again. Yeah, so we find, yeah, this is the SDR receive architecture. Okay, there we had the transmit architecture. In the receive architecture, we find again these type of inputs which are given, and based on that, okay, we are now segregating these 2. And let us see, now go up again and you can see the results which are okay. Please go up. Yeah, this is the receive architecture. Please still go up. Still go up. Yeah. So, so then, no. Please come down, sir. Please come down. Please come down. No, you have to go up. You have to go up. Yeah. This is the receive, SDR receive architecture. Just come down a little bit. Oh, you got. Okay. Still down. Still, you can go up a little bit. You can go up a little bit. Still go up. Yeah, you can go up. Still go up. Little bit up, because I want to show them the spectrum of, anyway, the results are there. Anyway, this we are able to show, it's all there in the paper. Spectrum of the CDMA signal at baseband. So what we did, we simulated the whole condition at transmitter, configured that in SDR. Similarly for the receiver, whatever we sent as whatever we conceived as the 2 signals at the transmitter, the same thing we are able to receive at the output of the receiver. Okay, so let me just go up a little bit. Can you open this portion of conclusion, sir? Can you make it a little big so that I can conclude from this paper? Just take it up a little bit. Yeah, you can bring it down. Yeah, conclusion. Just take this up. Yeah. So what we say from this paper, the receiver model is outlined for the BTS to interoperate between GSM and CDM in a very practical way. We have taken all that. And for the practical case, the capacity of BTS in a cell will be more than 2. So the bandpass sampling algorithm for N bands can be used to calculate the sampling frequency for the ADC and the IFs for channels more than 2. So the BTS can simultaneously work, as we are seeing here, for both GSM and CDMA. And in a similar way, the transmitter model can be worked. Here we have shown only the receiver model. The flexibility of the SDR is that the same can be extended for any other standard. Okay. So can we go up, sir? We can show some of the important references which the students can use. Can you just go up? Can you just go up? Still up, sir? Yeah. So these are the standard references you could see. And this Uptech House is a very nice publication. What I wanted to draw your attention is to a conference publication which we did in 2009 with with an international conference here when first this idea came. And then can you just go up a little bit, sir? Yeah. So this was the other one which this was with Velour, but in the other paper we have got the 2009 publication with what is that, wireless VT. Okay, so that is where this whole result. So in a nutshell, and again this is a very good book, I want all of you to follow. Raymond Steele, Gold and GSM CDMA 1.3G system. So please see that this book is available in your library. It's a very good book. Okay, and of course we got a lot of input ideas from this paper which they had published some time back, Prakasam and Madheswaran, where they used this technique for automatic modulation identification, which can be used in SDR. So that is again a good research area. Okay, so with that background now, I think we have given, and we have got a variation of this paper where is the second paper. So we won't go to that now, sir. We will straight away go to the PPT. Okay, we will go PPT because that's just a variation of the paper. Okay,
okay sir. Okay.
But very authentic, and students can use it and get a lot of newer ideas and take up new publications. Yes. So you can go to the slide mode. So this is basically the PPT representation of it. So as we say, GSM belongs to one system, CDMA belongs to another system, and you want to have interoperability between two systems. So as our student was asking, what then is a very important application? Here then we are showing it live for you. That is interoperability between GSM, CDMA using software-defined based transceiver station. Go to the first slide, sir. So this is something which we have. Now you are very comfortable with this definition here. Again, reiterating the same point, same hardware for different application, just by changing software. What are the advantages which you can note down here? Lowering network infrastructure costs for operators, easy for upgradation, multi-functionality. Okay. Next slide. So on the SDR architecture, we find what are all the systems which are existing. We have an analog subsystem, we have a digital subsystem, and then we have the reconfigurable part in the SDR architecture. Okay, so the analog system consists of, as I said, antenna, RF filtering, receive preamplification, transmit power amplification, reference frequency generation. So these are all things which are existing in the analog domain. And on the digital subsystem, we have up and down frequency conversion to baseband, IF filtering, modulation, demodulation, and of course the reconfigure. So this is basically identifying the various subsystems so that it will be easier for us to operate, put them all together, and in a holistic manner try to look at this. Next. So now this is almost what we have seen in the paper, the SDR receiver, digital front end. So from the analog to digital converter, we have a down conversion which is happening in the I channel. We have then Q is the quadrature channel, the I and Q things, because these are all required with the FIR filter, okay? And this is the numerical control oscillator, okay? Which is the equivalent of the local oscillator, which we have in the receiver here, and this is the demodulator, and then from the transmitter, this is going into the receive section here, okay? Next. Now we look at transmitter. So from DSP, which is basically the DSP is the place where you do all the source coding, okay? Channel coding comes after the antenna here, where we use turbo codes and all that. Source coding comes here, okay, when you're doing source coding on your speech or whatever type of, whatever channels you're giving. So I have the modulator. Once again, we have the optimum use of the FIR filter, and then we are up converting, once again, numerical control oscillator, which is playing a big role here and enabling this. And from here, we are now going to digital to analog conversion before it gets into the antenna portion. Next. So the design aspects are what do you need? Look at it. This is a solution. It's very useful for students when you design your PPT. What you need, you place on the left side. What you want, what is the solution, place it on the right. So the design aspects are placing the ADC DAC as close to the antenna as possible, and then flexibility of the receiver. Okay, and the solution is we do bandpass sampling and automatic modulation identification, which we have utilized in a very way, which we have shown in the paper here, which we are doing the implementation here, so that is the proof of the pudding. Okay, it's not sufficient that we write those theoretical papers, but then we have to implement that. That is very important. So after the design ideas were thought of, we first did the implementation, then wrote the paper. We don't write the paper and then do the implementation. So we verify everything, we are fully convinced, and we got all the diagrams pertaining to it. Then we are able to put the paper, which gets a lot of recognition. Next slide. Now we talk about bandpass sampling, basically because the idea is from the antenna when the signal comes in, we are having a very big requirement because we want the ADC to operate at a level at which the data rates are quite reasonable at where we can make it function. By using this bandpass sampling technique, we are able to convert that in a very elegant way. Let's see how we are able to do this. Next slide. Yeah. So what happens, this bandpass sampling, this method allows us to down convert analog bandpass signals to baseband at a low intermediate frequency, low IF digital signals without analog mixers. That is important. We are not using any analog mixer. That means a simple method that down converts analog bandpass signals to baseband or low intermediate frequency digital signals without using analog mixers. So what happens? What is the need for bandpass sampling? So this is the reason why we do this. Again, we are reiterating this point. For most radio application, if Nyquist sampling is employed, the required sampling rates for ADC would be impractically high. Like I took the example for GSM, that the frequency is 900, the Nyquist sampling rate, it is 900 megahertz. So Nyquist sampling rate comes to 1800 megahertz or 1.8 gigahertz. It's a very, very high frequency as far as ADC is concerned. So it's unnecessarily wastage of resources and handling and all that will end up into a lot of problems. So we use this elegant technique and overcome this. Next slide. So the steps involved, what we do is determination of all possible orders of spectral replicas in the spectrum of the sample signal. For each possible order of spectral replicas, its valid sampling frequency range is determined. For a particular band of incoming signals, there are many possible valid sampling frequencies. So these are things which are involved. We look at this very carefully. From this, we try to optimize and choose what would be a good frequency of choice is what we have made here. But we didn't arbitrarily do it. Went through the steps. From there, we picked up the relevant ones. Next. Next slide, sir. Yes. So now that tells you ranges of valid sampling frequencies for two different standards, GSM 900. So these were the two channels which we have chosen in GSM, 890 to 890.2, 900 to 900.2. We could have chosen anything else, but this is what we have chosen. Similarly, for IS95A, which is a GSM, which is a CDMA system, we have chosen from 824 to 825.25, 840 to 841.25, and the sampling frequency range you could see in megahertz what it is ranging from 0.8165, okay, 079. So these are all various sampling frequency ranges from which an optimal one has been chosen, okay, for the next stage of operation. Next slide. So determination of IF, okay. So what we do here is any frequency lying within the valid frequency range is chosen as the sampling frequency. So the value of the IF, the down converted signals, is given by these formulas here, okay. So if it is even, if it is odd, so based on that, we go to the next slide. So the sampling frequency chosen and the values of down converted IF, okay. So when we choose 0.8165 megahertz, okay, IF in hertz was 10,000. Okay, yeah, 1051 and 307082. Okay, so these are IF1 and IF2 frequencies chosen. Okay, for the sampling frequency. Out of that, we take very appropriate ones and then do the subsequent conversion for implementation ideas. Next slide. So we consider two bands in GSM, two bands. So for the two GSM bands, sampling frequency range is obtained as 51.44 and 52.35 megahertz. Okay, next. And this is the spectrum of the two GSM bands, 890.1 megahertz and 900.1 megahertz. Okay, so this is the spectrum of the two GSM bands. Next. determination of IF, okay, 51.44 megahertz as sampling frequency. IF1 comes to 15.62 megahertz. IF2 comes to 25.62 megahertz. And these above values can be verified from the actual spectrum of the sampled signals. So now we'll go and have a look at, this is what we got. We'll check what is the sample. So you could see how the IF1 is at 15.2, and here it's a little bit obliterated, but you could see that exists. 25 spectrum of down converted bands. Next. So now, because I'm not repeating this for the other signal IS95A, okay, because we are done for. So now we go to automatic modulation identification, AMI, which we took in that second reference from that paper. Next. Automatic, yeah. So what we do is, here we are looking at, as I told you, because we've got two different modulation techniques, what could be the technique to identify. So we have chosen this method of distinguishing between Gaussian minimum shifting and quadrature phase shifting using the wavelet transform. So this is used in the front end of the SDR receiver in identifying the incoming signal and configuring the receiver correspondingly. Okay, because if you have a GMSK signal, automatically that type of signal should go into that slot. The QPSK will go into the opposite slot. Next. Next slide.
ठीक चल काट दे
Of course, here the steps are transformed, what it is, extracted coefficients, the histogram, what it was plotted, was mentioned in the paper, same thing. You can skip this, you can quickly go through it. Next. Single peak is QPSK, multiple peaks is GMSK. We'll see a diagram of it now. Yeah, this is GMSK. You can see multiple peaks in the GMSK histogram, and because it is easier for the system to distinguish. Now let us look at CDMA. That is QPSK. Let's see a signal. Okay, so with this background, now it is sent into the next slide. Go to the next slide. Oh, I think we skipped the results. Probably they are coming together, sir, in that. Can we, I think some.
No, this is the one, sir. This is the one only.
Yeah, that's all. I think some slides, it's there in the paper. So what is very important here for the students to remember is that that automatic modulation identification. Through that, we are able to identify, segregate, and once it goes to the receiver modules, automatically we are able to get at the output the two spectrums, the spectrum of the the GSM signal and the spectrum of the CDMA signal. So we can see how, using software-defined radio techniques, we are able to make both the systems coexist under the single system here, and depending on the requirements, we can switch between whichever system. This is not restricted to 2 systems. We can have even 4 systems or 5 systems. Today, we started this research in 2009. Now it has become much more automated and much more versatile. And tomorrow's lecture, we will be seeing the WANU software. Okay. The WANU variations on different applications which are used in a lot of this cellular communication areas and for other applications. So I'll be discussing that, and with that it will complete. Okay, so here I will stop my lecture today, sir.
Thank you, sir. Thank you.
We are almost on time. We will take some questions. Somebody was asking some nice questions. We'll take it one by one. Just give me a minute.
Yes, yes, yes.
Yes, sir.
So participants can ask, you can unmute and then ask the question, because sir is not looking at the chat box. Any doubt or any question you can put directly.
Yeah, they can even send it by mail. Not a problem.
Yeah.
So, but if they want to send it on chat box, is okay, sir. I can see it also. Not a problem.
Okay. So one,
So on this
Yeah.
more, if I press more, the chat box thing comes. Okay.
yes. So one participant has put one question, sir, that can
They were
you
having some
explain?
question. When I was giving, somebody was asking some question on RFID. Can I get?
Yeah, that is the one. So he has asked whether RFID localization, some examples of RFID localization.
What is it that they want? RFID?
Localization.
RFID localization.
Yes.
Okay, they want to use RFID for localization. Now,
Some example of that.
no, please remember, RFID is a tag. It's just a tag. Now, RFID comes with in two compartments. It comes. We have passive tags, active tags. Okay, so RFID will be more appropriate when we use for logistic application. That means we can use an RF tag in the transmitter side to identify that so and so person is being involved. But for us, what is it that we wanted? We wanted in our context server system, we wanted to get information. See, the RF tag can be used for positioning for at that transmitter point we can. But this RF tag should also have a provision to transmit. So if it has this capability of receiving and transmitting, then we can use it for some of our application which they want. But then what normally happens is in retail stores, in malls and so many other areas which they have, they normally use this RF tags for passively identifying a particular a packet or a particular transit, or let us say you are picking up a library book, something for that type of application. But it is not very elegant for us to operate the RF tags in the localization environment. Instead, what is more elegant for us is just with your cell phones today, because they have Bluetooth, they have UWB, they have Wi-Fi, they have all the other things. With that itself, we can maneuver and do many of our operations. Okay, using the RF type of localization. But definitely, if one is very interested, we can always use RF tags for some of these applications. Any other questions you have, please?
One is asking how we can use the RFID tag in car parking system.
RFID tag, the RFID tag for car parking will be a very, very coarse system. It will not be a very elegant technique. You see, this RFID is something which is existing, that's all. But then this particular system will not be very accurate in its estimation. Yesterday we have shown using the GCC algorithm and UWB, we are able to get identification accuracy to the tune of 3 to 4 centimeters. So the RF tag in a very generic way is something which tells where exactly is that type of thing, but for you to accurately position that, okay, because there will be tags which will be identification points where we will use RF tag principles, definitely. But for you to accurately park, we have to utilize this. So the RF tags will be more utilized in that car parking window handrails. Okay, you see, remember there are handrails in front of some 6 cars. So there these tags will have this RF type of capability where they can transmit and receive. So we could have some of these tags built inside, okay, inside the car, from where they can communicate with that transmit receiver on the handrail. And together, after the car is parked or before it takes off, it can get guidance. But for it to make it park at 3 centimeters or 4 centimeter accuracy, it becomes very difficult. The tags cannot be able to do it. There somebody is asking some other interesting question. Yeah,
Yes,
somebody
sir.
is asking, can
Yes.
cell phone read RFID? No, it is something like, you know, you have, what is it that we have these days?
No, one is
Credit
asking
card,
that whether
credit card, we have, what is that other thing which they are using now? This Chinese system. You know, all the markets are using, what is that? Suddenly I not able to get that name. You know that diagram we have now when we visit Reliance, that we are able to pay that amount to procure. What is that? So in a similar way, they can use this for that application. See, we can, that is basically with a reader. You know, remember that Paytm, sorry, I couldn't get that word. Paytm. See, in Paytm, we have got a Paytm reader in our cell phone now, right? So similarly, we can build an RF tag reader. I think that will answer his question, right? If you want to use that application, we can build that.
And one more is asking that this SDR is consuming more power and resources as compared to the other systems.
No, can you repeat, sir? I'm not able to hear that question properly.
This SDR system.
What is it, sir? What is the question?
SDR require more power and resources as compared to system especially designed for different technologies like GSM, CDMA, and others.
No.
SDR
he is asking whether SDR will consume larger power compared to CDM.
Yeah.
This question is, in a different sense, he's asking. See, SDR is something in a CDMA system. We build an SDR so that it can interoperate CDMA with GSM and all that. So SDR is not getting compared with CDMA or GSM or something like that. SDR is an additional software platform which is got configured for it. And anyway, all the software which we are using to enable this type of additional operation consume very little power. Please tell him it consumes very little power. Whereas your CDMA base station and GSM will be of kilowatts of operation. This will be hardly milliwatts, okay, maximum. And even this particular power consumption will be much less. Okay, so you take a GSM station, that itself will consume maximum 200 watts. It doesn't go to kilowatts and all. So it will be very, very less power.
And
So
one more question is from one participant.
Yeah.
What is waveform in software-defined radio? So just I want to confirm from the participant that what does he mean about the waveform? Something he has written. What is waveform in software-defined radio? So the answer you can unmute and you can ask directly. सुधांशु कटारे,
what is the question, sir? I couldn't get.
what is waveform in software defined radio?
What is the platform?
Waveform, sir, waveform.
Waveform. Okay. See, the thing is, now it is not, I don't know why he asked this. You see, when we are doing this software defined radio, when we are conceiving this, please remember at the end of the modulator, there's a particular waveform. At the end of the filter, there's a particular waveform. At the end of any other, at various levels, you have different waveforms. It is not a single waveform. And that waveform is the one which we transform into via a software. That is, using that mathematical ideas, we are able to write those equations to depict that software. So it is not one single waveform for which that software is done. This software is a combination of the combination of various waveforms is this software. Okay, so each one of that blocks which was there in hardware, now using a mathematical technique, we have converted into a waveform, and from that waveform we have written a software which has configured this software. So finally we are functionally able to do that type of hardware operation via this software, but giving rise to that type of a operation which is required by that hardware. If that hardware was there, it would have done that operation. Now we have replaced that hardware using our mathematical function by which we have brought out a mathematical equation from where a waveform has come, and that waveform we mapped it into a software. Okay, so it is not one single waveform which comes with software defined. It is multiple type of a thing, and the elegant thing is that we have been able to completely represent the radio receiver in a mathematical functionality, and from that mathematical functionality we have generated the software. So that is how this software defined radio has come about, and with it comes whatever accuracy or whatever limitation which comes with that system. We'll have to live with that limitation. Okay, does it answer his question?
Yes, sir. It cannot be a single waveform. There may be many more waveforms inside.
Okay.
Okay, anyone else? What are the techniques for security in software defined radio? One is asking, sir, what are the various techniques?
Yeah, nice question. He has asked a very nice question. So there are various techniques. The first question is, when you generate the software, see, please remember, when the software is already developed and kept in a cloud platform, right? When you generate that software, the first requirement is it should be virus free. No virus can exist. See, today you are getting a software for the establishment of a software defined radio for a CDMA application. Somebody has developed it. You straight away download it, and the technician comes and installs it. Obviously, there will be virus, and maybe day one it is not there, day 5 it will be there. So it has to be virus free. Then the second platform on which it depends on what layer you want to do it. Are you wanting to do this implementation? Because most of our SDR is at the physical layer. So at the physical layer, we have different levels of software security things. One of the very elegant systems at which we can do this type of a thing is if we are able to segregate and implement this at the RF front end, the security. Okay, if you are able to build that, you are not enabled. You will not be able to allow anybody to come inside. Okay, so you can bring you can build that security aspects at layer 1 or layer 2 or layer 3 subsequently, but you can do that. Now let me give you an example at which people are now doing in 5G. 5G. I want all of them to refer to something called RF antenna fingerprint. RF fingerprinting. Okay. is a new technique. That means if you look at a 5G antenna, which is a phased array antenna, they are able to build security at the antenna point itself, which none of the hackers can get inside. So they have something called an RF fingerprint. They are able to map that so well, and this system protects this beautifully at the physical layer. To that extent they can go. So depending on where you want to do it, at what layer you want to do it, because a lot of security things are there, so many of those ideas can be brought in and you can develop it at different levels. So, but if you protect something at the front end itself, subsequently they are all very well protected. Nobody can get inside. Yeah.
Any other participants?
Yeah, now I have 2 points to, yeah, somebody's asking, no problem.
Please unmute and then you can ask. Sir is having vast knowledge and experience. So,
Sir, I would like to end with the 2 points which I want to make.
yes, sir.
So our students, any of them have taken training in BSNL or VSNL or any of these places they go for that is on-campus training, no? They go to do their
Right.
internships and all that. So all of them would have seen a BTS. So now this BTS, if it is not in the city, suppose it is located about 80 kilometers from Bhopal on the way when you're going somewhere. Suppose this is a BTS. Now, one of the biggest problem with all these BTS which throughout the country they are having is all these BTS are powered by, where do they get the power? BTS. Today, people want internet connection. They want TV connection. They want so many other connections which they see, right? And the biggest problem with all these BTS is they are powered by diesel generators. These diesel generators generate million tons of carbon footprints. So today, biggest problem is pollution with this type of system, right? Now you will find they have thought of, now luckily Bhopal has got a very good solar system, powered system. So we will look at this type of capability now to replace the diesel generators by these solar capsules, right? So that we will be able to see millions and millions of gallons of these diesel is being used for all these, powering all these generators. 70% of all power for BTS is done by diesel. And today, Government of India pays crores of money on that. So one of the elegant systems which we can, now with the entry of SDR where power and all these comes down a lot, we can use simple solar powered systems or wind power systems to take care of the power requirements, or battery powered systems to take care of battery requirements, and which is going to be exploited. Already they are exploiting in 4G and 5G system because they don't have this large power. Unfortunately for us, when we entered 2G in 90s, early 90s, the whole system, Nokia or Ericsson or whatever it is, they took the foreign system which was existing at that point in time and exactly they copied that here for us. That is why it is a big handicap for us that we are not able to get away from these systems. Otherwise, India would have saved crores of money. Crores of money. This is what we want our youngsters to remember, that they should be able to look at elegant systems by which we can power. And thanks to when we are using SDR, they all consume very little power and very elegantly. And Bhopal being now center of attraction because the solar power thing which our Honorable Prime Minister has inaugurated. It's a great tribute now which we get. Probably at Indore he has done this, sir. This,
no, one district called Rewa.
Eva. That is at Bhopal. It is at
No,
Bhopal.
it is far from Bhopal.
Okay, okay. Anyway, it's in Madhya Pradesh. That is
Yeah,
important.
it is Madhya Pradesh, yes.
It's a wonderful thing. And we would look at students, how they can use solar power to power such things in a very elegant way, or these days, the electric batteries, that is coming up in a big way, or the wind power things. But definitely get away from diesel generators, which are having lot of problems, atmospheric pollution, air pollution, carbon footprints, and we have been living with that problem for a very long time. So that was the point I wanted to emphasize.
Thank you very much, sir. So in front of you, our students and other faculties are not having the dare to ask the question. So that's why they are keeping quiet. So they may ask later on by mail. They can send, or they can. Thank you very much, sir.
Thank you. And then tomorrow we will take up the last portion.
Yes, sir. Yes.
I would like all of them to look at VANU ways, VANU. So on that we would concentrate and give them newer ideas on which they can take up subsequent projects and more areas in which research and development concepts can be taken.
Right.
Thank you very much.
Thank you, sir. Thank you. You can leave, sir. So
Yeah.
I will be here. समझ में आ रहा है आप लोगों को कि नहीं, पार्टिसिपेंट्स?
यस सर,
आ रहा है? वेरी गुड, वेरी गुड।
यस सर, यस सर, बहुत अच्छा लग रहा है सर।
तो आप कुछ नया करें अपने मध्य प्रदेश और अपने यूनिवर्सिटी के लिए।
यस सर, सर सिविल इंजीनियरिंग फील्ड में सर कुछ हो।
क्या पूछ रहे हैं? आवाज कम आ रही है आपकी।
सर सिविल इंजीनियरिंग फील्ड में सर
कौन
सा टोपोलॉजी यूज करेंगे सर?
सिविल इंजीनियरिंग में मींस इसके बारे में, वायरलेस के बारे में बात कर रहे हैं आप? किसके में?
ये सर जैसे कि सर रिमोट सेंसिंग के बारे में सर होता है।
राइट, रिमोट सेंसिंग।
यस सर।
तो सिविल में तो बहुत ज्यादा यूज है रिमोट सेंसिंग और आपके वायरलेस का। And nowadays people are working on सिस्मिस, जो आपका भूकंप जो आता है उसके ऊपर बहुत सारा काम चल रहा है और रिसर्च एरिया है वो अभी।
यस, जैसे कि कल्टीवेटेड यानी हाईलैंड एरिया पे हम जाके वहाँ पे रिसर्च नहीं ना कर सकते हैं, तो हम लोग रिमोट सेंसिंग के थ्रू ही ना काम कर सकते हैं सर।
राइट।
जैसे कि पहाड़ हो गया, हिल्स हो गया,
राइट,
जंगल हो गया, उस सब में से हम लोग जाके नहीं देख सकते हैं।
So there you have to put a sensor and then do the remote sensing only. So वहाँ से जो भी सिग्नल आ रहा है उसकी प्रोसेस करके आप पता लगा सकते हैं क्या है। ओम से हमारी पूछ रहे हैं कि सर्टिफिकेट तो मिलेगा, सर्टिफिकेट, लेकिन उसमें टाइम लग सकता है थोड़ा सा, क्योंकि प्रिंटिंग और ई सर्टिफिकेट बनेगा और सभी को मेल पर भेज दिया जाएगा। तो आप अपना, हम एक फॉर्म भरवाएंगे, उसमें नाम और अपना ईमेल एड्रेस सही से लिख दें तो आपको मिल जाएगा सर्टिफिकेट। ठीक है, तो एनीवन एल्स?
थैंक यू सर।
तो बंद करते हैं मीटिंग। टुमारो वी विल मीट एट 11 o'clock।
यस सर।
थैंक यू ऑल।